Okay, today's lecture, I will continue to talk about newspaper search, but the topic will be the billion scale newspaper search. This slide is also from the CBTI 2023. Okay, from the tutorials. Okay, so this authors Martin is a professor from the IT University of Copenhagen, Denmark. And so it's short bio about Martin. So develop some famous systems, also also host a very famous billion scale alien challenges. Okay, so it's a recap for our newspaper search. Okay, so the approximate newspaper search pipeline, we can divide it into two parts. This one is build your database. Okay, so given a data set, and we will build these index structures. It usually take several hours to build your models. It depends on which index model you want to do. For example, if you choose to build a graph structure, it's very big, so it will take several hours. But if you are going to do a simple like inverted file index structure, so it would be faster than graph-based structure. Okay, so after you have done to build your data set, then you can perform a search. So the search is given a query vector here, and then we will perform a candidate search selection. Okay, here we will select a set of candidates from our graph structure to recall our lecture in last week. We present how to do the search in a graph structure. Okay, so you will scan a set of candidates and then find nearest neighbors to the query. And usually the query process spends just milliseconds, but it's very fast. Okay, so this is the competition, the challenge they held for approximate nearest neighbor search. Okay, there are several tests, several tracks. First is the median scale. Okay, so for median scale challenge, they use 1 million vectors from growth. Okay, so word embedded data set. Okay, so here we show this chart. This plot show you some dozens methods. They during this challenge, and the performance shown in this plot. And you can see the horizontal axis means your recall. Okay, so recall you see it's getting better from left to right. Okay, so you can see it's very accurate. The recall will achieve. You see it's the 1 minus 10 to the minus 5. Okay, so it's a very small, just a 0.99, very small. And for your vertical axis is your throughput. The throughput is the unit they use is a queries per second. It means how many queries you can process in a second. And so you see, if to the up level, it means your speed is very fast. Okay, for example here, it's 10 to the 5th. Okay, so you can process about 10,000 queries per second. Okay, so it means that if your curve, your results is to the top right, it means that your performance is very good. Okay, so it's a general, some dozens methods the performance shows here. Okay, I just give you some some points, some key points here. Okay, you can see there are some methods they are highlighted with pink color. This means they are graph-based method. Okay, all these methods they ranks from high to low. So this means the best one here, the second one, the third one. Okay, they just give some evaluation. Okay, so to rank this method, and it's clearly you can see that almost the graph-based method they have a better performance than the others. Okay, you can see they really perform very good than other methods. And also some methods they are highlighted with green color, which means is service. Service means there are some companies that provide such a service. They also join this challenge. Okay, so I think these companies, their performance is they have to charge, and so you have to pay, but their performance is not the best. So if you can write the code, you know how to integrate the systems. Actually, you can build your own system and achieve a better result. Well, generally you can see in medium scales, I think the performance is quite good. Okay, then you have a very good quality code, and also your throughput is very high, generally. But now another track, the second track is to expand to billion scale. Okay, to billion scales. Let's say, okay, we use the same tools to the medium scale, so we build the index and search only on a single thread, and give you 2 hours for all the competitors. I give you 2 hours, and after 2 hours, I will kill your containers. You cannot do anything. Okay, so just give you 2 hours to build the database. You need to perform the query. Okay, but actually, it's very difficult to do the competition because it takes a lot of time. Your data set is scaled up to 1,000 times. Okay, so from million to billion, your data set increased 1,000 times. So it's only use 2 hours to build your data set and to search your queries. It's not enough. So there are some teams they ask to require more hours, for example, to extend to 24 hours. Okay, because they think they cannot do a very good result just using 2 hours. The result is very bad. The record is very, very low. Okay, so they ask. Okay, so I think after that they can adjust the rules. Alright. So and maybe you think, if I extend the 2 hours for medium scale competition, for the billion scale, maybe I have to give them 20 to 2,000 hours. Okay, but it's impractical. Okay, so okay, it's their final result. Okay, it's a NIMS competition in 2021. Okay, you can see these 3 plots on 3 different data sets on big ANN, NS Turing, and deep from billions. All are 1 billion data set. And they just show some result here. And okay, let's see the conclusion. Let's say many methods they did not improve the baseline too much. Okay, so you can think the face. Suppose you can treat the face as our baseline. Okay, so you recall, you see, it's much lower compared to the medium scale data set, right? Now you can achieve just about 0.8. It's your upper bound. unlike the median scale you can achieve 0.99. Okay, very high. But here, everybody's method, and you just can achieve 0.8. And their throughput query per second is also down to maybe just 20,000. Or this depends on what the data set you use. Okay, but you can see their performance not improve too much compared to some baseline like face. For example, you can see the original one is face here. Here, this one is the blue one is the face method. Okay, so I think this method still have a space to improve a lot. Okay, so today's lecture I will give you some roadmap to tell you under what conditions, which strategy you can choose to do your approximate mean research. This is the roadmap. Okay, so first you can consider here. Okay, so in this slide they don't consider the following three cases. First, non-CPU architecture. They don't consider use the GPU or GPU, and they can just consider CPU. And the second is the query capabilities. Okay, it means we only consider we don't consider the range query or the filter query. The range query means I will give you a range. So every data points, if the distance to the query is smaller than the range, I will retrieve it. Okay, so it's unlike the traditional approximate mean research, right? Approximate mean research can be divided into the two parts. One is the range query. You want to find a range according to your query, and the second is just to do the sorting to retrieve the k-means neighbors. Okay, they are different, but in this competition, in this talk, they only consider the k-means neighbor search. They don't consider the range search. And also the updatabilities of the index. This means that sometimes the data will be updated, like in database. Database you will add or delete some data points. Okay, but in this case, they don't consider this case. Okay. It's just when you build up, your data set is fixed, it's done. It will not be modified anymore. Okay, so under these considerations, the roadmap is like this. Okay, first we consider your data can be stored, all the data can be stored in your array. Okay, if yes, this means you have a lot of memory, or you have a lot of arrays. Okay, then you next, so you want a high recall or not? If yes, you should consider the group-based element. There are some methods you can choose. Okay, if not, if you don't want a high recall, okay, you can consider other methods like the IDF, inverted files, or you can choose the face, IPF, or others. Okay, it's the upper method. And for the other way, if you cannot store all the data in your array, okay, you have to go to another pathway. Okay, then the next question is you want a high recall. If yes, okay, you can consider because it's you don't have enough array. Okay, so you have to compress your vector here. Okay, so the compressed vector with your graph or some structures like this, and it can help you to handle if your memory is insufficient, but you still want to achieve a high recall. But if you don't care too much about your recall, Okay, you can use the IDF, build the IDF compressed vector. Okay, so it's a general roadmap about the billion scales to handle the billion scale data set. There are several billion scale data sets. So here you can see a big ANN base. Okay, the Facebook or Microsoft. Many of them they release the billion scale data sets, and they have different data types, dimensions, and they use they also prepare some best data, sample data, query data, and ground truth. Okay, the best data is 1 billion data set. It's a complete data set they release to you. And the sample data, we usually use the sample data as your learning set to train your model. And the query data, okay, they will give you as about maybe 10,000 queries or 100,000 queries for you. And each query they provide the ground truth, the correct answer. Okay, the correct answer may be provided for each query, provide you 1,000 news neighbors for you. The data is the data ID is from your base data. Okay, so you can see some data sets. For example, this one, the text to image. For these data sets, okay, it's used floating 32. It means use 4 bytes to encode the dimensions. Each dimension is a real value. Okay, so it use 4 bytes to encode it, and it contains 200 dimensions. So it means in total 1 billion text to images descriptors. You will use 800 gigabytes. Like too much, right? It's difficult for you to store, even for this small one. It's Microsoft Space D. It needs 100 gigabytes. Okay, so I think it's very difficult for if you use just personal computers. So how to handle the 1 billion is very critical to challenge your computer's capability. Okay, so let's start from the first pathway. So we want we have a high resource and we want high code. Okay, so possible setup maybe you have a very high end the CPU and a very large RAM from the 200 gigabyte to 2 terabytes. This is the paper they use to do and this paper is to tell you try to do some experiments, comparative analysis. This means they run maybe dozens methods and on the billion scales data sets. And what's the machine they use? Okay, you see they use the Azure. The Azure is I think okay, very high-end machines. It takes you about maybe $400 per day. Okay, and there's a low-end machines. Okay, still take you $144 per day. Because I think it's more than my 1 day salary. Okay, so they are very expensive. Okay, so these papers, I believe they burn a lot of money to do this experiment and give you an analysis to tell you what's the performance evaluation comparison between these methods. Okay, so let's go to the first pathway. Okay, we will build to try to scale it up from million scale to billion scale. Okay, let's recap our graph-based approach. Because if you have enough memory and you want to retrieve a high code, the graph-based is your first choice. Okay, so in graph-based index structure, in here, all the data points, they are vectors, and they can represent like a node here. And we will build the edges between the neighbors like this. And the connection between the neighbors is basically to connect your nearest neighbors at similar points, and we also hope the direction, the connection direction can be diverse. Okay, to different ways can be diverse. And how to build the database, they usually follow an incremental way. This means I will insert a point to the current graph, and then find these neighbors to build the edges. And the next, I will build the next point, maybe the x 92, maybe here, and then I will base on this current structure to build the edge. And then it's x 93. I will insert the point one by one. Okay, it's called an incremental build. Okay, so it's a general way to build a graph-based structure here. Okay, so the index size is usually, it's very big, but there are some parameters you can choose. This will influence your structure size. As the main is how many degrees of nodes you want to connect. Okay, so this means how many neighbors you want to connect. If you want to connect more neighbors, your index size will be large. Okay, so and also it will influence your build time. If you want to have a faster build time, maybe you have to use a smaller degree, or a small big search width. Okay, but this means you have small neighbors, and it will influence your record, your search accuracy. So if you want to achieve a high accuracy, your trade-off is in your search time. You should have a wide search bins. Okay. This means you have to find more candidates. Okay, any problems? Here they show the algorithms you can do the parallelized insertion. Okay, so it means if you have many points you are going to insert, okay, you can do it because you have many CPUs. Okay, you can do it at the same time. You don't need to do one by one. You can do it maybe. You can do it parallelized. Okay, so it's ideas. I think it's you can refer to the algorithms. Okay, there are some parameters you can consider in here. And to build your index structures, okay, your degree bound R, okay, it will determine your index size. And also your bin width. When you search your neighbors, you have a bin. You have to set up your candidates, how many candidates you want to keep. Okay, so the parameter is called L. Okay, if you use a large bin width, you will have beta neighbors. Also the forming factors, we hope you can say it is alpha. Alpha is to control the diversity of your neighbors. And in your search state, okay, you only control these parameters L, the bin width. It means how many candidates you want to keep during your search phase. Okay, so here is a conclusion. I hope you can, it's a summary about this method. In this method, okay, you can, if you want to It depends on what's it's your purpose. Okay, so you can choose the degree, your beam width, or your permit factor. Right? But they are very difficult to choose. And each time when you change your parameters, you have to spend several hours to do it, to do the build. And then when you perform a search, sometimes it's difficult to analyze which parameters influence your accuracy or influence your search time. It's difficult to analyze it. Okay, so it's the main problems of this method. Okay, here I show some result to build the data set. For example, the disk ANN is a very famous method. Okay, so it is general parameter set up on different data set. You can see, for example, in NS space E, in this data set, a disk ANN they use the following setup for the parameters, like this degree bound is 64, and its beam width search is 1028, and then alpha, the parameter, the pruning parameter is 1.2. Okay, it's a standard configuration for these parameters. Okay, so generally, in the billion scale, the index size will depend on how many neighbors you connect. It's like the 4RGB. R is your number of neighbors you connect. Okay, so in this case, if your neighbors are 64, you will need how many? 256 gigabytes. Just store your index function. Okay, remember to store the data in your memory. You have to keep the index structure and also your raw data. So here we didn't count the raw data. If you include the raw data, it's about and remember MS space D is about 100 gigabytes. So you have to plus 100 gigabytes with 256 gigabytes. So in total you need more than 300 gigabytes. Okay, you have to spend so many memories to store your data. Okay, so this graph shows build time on NS space D. Okay, so you can see there are several methods. Their build time here. When your data size increase from 1 million to 1 billion. Okay, they find that actually the growth, the build time is growth linear. Okay, so it means if you have 10 times increase your data size, but your build time is just about 11 or 12 times increase. Okay, this table shows the overall build time. So you can see actually they spend more than 10 hours for this ANN, but for the phase or the field count they spend less time to do the build. Okay, you can also perform the parallelized search because you have multiple CPUs, or multiple threads. Okay, each thread or each CPU you can perform a query, to do the search. Okay, so the parallelization is just over the queries. Okay, so here finally we show the result here. This is again several methods, and we show data from the 1 billion, so 1 million data size to 1 billion data size, and here the y-axis shows the query per second, the throughput. In general, you see. Okay, I think the conclusion is when your data set is increased to 1,000 times, but your query is just 2 times slow. So it's lucky we don't slow down 1,000 times. just slow down twice. Okay, so I give you a summary about this method. Generally, this method means we load all the index structure and the data in our memory because we have a lot of memory, and we use the graph-based structure to do an index. Okay, it can achieve a very high recall and also a high throughput. The advantage, okay, you can see if all the memory can handle the data, okay, it can be a very good scaling of your candidates. Okay, so you can see in these figures. I want to let you know here for this method, you can see the original one. For this method, when it grows from 1 million to 1 billion, okay, its computation cost increase just not too much. Okay, and you can see it only change 0.0001% of the data set. So this means this method only check 1,000 data point is their candidates in the 1 billion data set. Only 1,000 candidates are checked. Okay, so it's very efficient. You don't need to check 1 billion data, only 1,000 to be checked. Okay, you can save a lot of time. So it's a very good advantages for this method. But talk about its disadvantage. Actually, okay, we have mentioned that the parameter is difficult to choose. Okay, so and also it's difficult to predict its performance. It will influence your search time, your throughput, or your recall. But it's difficult to know how to make a good trade-off between them. And to build your index structure will usually take a lot of time. Okay, so it's the main disadvantage for this method. Okay, any problems? Okay, so here they recommend you to use this method called disk ANN. Okay, so disk ANN is published by Microsoft India. Okay, so this method they also release their code. Okay, so if you are interested about if you have enough memory and you want to use it, okay, you can try to study the disk ANN. We will talk about the method, the detail of the method later.